In this video, we're going to talk about what we call the definite integral. Previously, we saw that if f is a rate of change of some quantity, then the left hand and the right hand sums approximate the total change in the quantity. And so when we did the left and right hand sums, we were using areas of rectangles and adding those up to give us that total change, that approximation, right? And so sometimes we'd use like 5 rectangles or 6 rectangles or 10 rectangles. But since larger values of n, where n is the number of rectangles that we use to make that estimate, since those larger values of n give more accurate approximations for the total change in the quantity, then we want to let n approach infinity as if we're using an infinite number of rectangles, meaning they're going to have a width that is getting closer and closer to 0 so that we can get the exact area. And so the definite integral of f from a to b, this is how we read this notation. This is the definite integral, and sometimes we take out the word definite and we say the integral from a to b. That a and b, so when we had a function before and we were calculating the area under the curve, from x equals a to x equals b. This is that a and b there. And we wanted to calculate this area. And so we could use our left-hand sums to get over certain intervals. And that would give us the approximate area, right? For a picture that looks like that. And so this a and b are the endpoints of that interval, right? So we read this as the integral from a to b of f of t dt. The integral from a to b of f of t dt. Now, this is already a derivative. This is like saying dy over dt. And so this denominator dt here is going to be the same as this dt here, so that all of this stuff works out. We like to say that dt tells you the variable in which you're going to integrate, kind of like when we do dy over dt. This tells us that the variable we're doing our derivative with respect to is t, all right? But in either case, that is going to be equal to the limit as n approaches infinity. We want the number of rectangles, the size or the width of our, the number of subintervals we're going to use to go to infinity. All right. And so another is going to be the limit as n approaches infinity of our left-hand sum. And so if we wrote that out, it's going to look like the limit as n approaches infinity of the sum from I equals 0 to n minus 1 of f of t sub I times delta t, right? This notation has some similar features, right? Notice there's an f of t here, but when we were doing our rectangles, we use f of t sub I. There's a dt here where we have a delta. This is like a d in Greek, delta t. Here, we have this Greek letter s or sigma, and then we have a sort of an elongated s here for basically a continuous area that we're going to be calculating. All right, it also equals the limit as n approaches infinity of your right-hand sum. And so we're going to do the limit as n approaches infinity of the sum from I equals 1 to n of f of t sub I times delta t, right? And so again, it's the same features, except we're using the right-hand sum. We're going from I equals 1 to n of f of ti delta t. And again, we read this as the integral from a to b of f of t dt. These integrals are usually equal to each other. They only differ by we're starting at 1 and going to n. Here we're starting at 0 going to n minus 1. As long as 0, the difference between starting at 0 and 1 isn't huge, these integrals are going to be equal, and they generally are. Each of these sums are called Riemann sums, right? And so if we let our sum go to infinity, this variable n go to infinity, then we call these Riemann sum after a mathematician named Riemann. The f in our integral notation is called your integrand, right? So this whole statement is the integral. What function you're taking the integral of is your integrand. All right, and a and b, those same a and b's from when we were using our rectangles before, when we use integral notation, we call these the limits of integration. All right, and so integration is the process of finding an integral. And so this is what we're going to start doing today. Now, we don't know, we're going to develop some of the algebraic type methods to help us calculate an integral. But for now, what we're going to do is we're going to use our left and right hand sums. We know we want to let n approach infinity, but sometimes we're doing this by hand, right? And so we can't do an infinite number of rectangles. And so a lot of the stuff that we're going to do today is going to look very similar. The only difference is that we're going to use integral notation now, all right? For example, in example 1, it says estimate the integral from 0 to 25 of f of x dx. The only difference here is my input variable of this function is x, and so we use this dx notation here instead of f of t dt. And we're going to estimate this using the left hand and the right hand sum if we're given this data here. And so let's go ahead and do this. Let's start with our left hand sum, right? So the integral from 0 to 25, that's our a and b, of f of x dx. It equals our left hand sum and right hand sums, right? When they're going to infinity, right? I'm going to do my left-hand sum. Of course, we can't do an infinite number of rectangles when we're given a table of values. And so I'm going to use my Riemann sum here. But I'm going to estimate it. I'm going to have I equals 0, and I got to use all the possible rectangles I can use in my table. Now, basically, I need to count the number of subintervals that I have because that's my n, right? So 0 to 5 is 1, 5 to 10 is 2, 10 to 15 is 3, 15 to 20 is 4, and 20 to 25 is 5, right? So we have 5 subintervals. That means n equals 5, right? And so if my left-hand sums run from 0 to n minus 1, I'm going to go from I equals 0 to 4 of f of x sub I times delta x. Now, my delta x is basically what I'm counting by in my chart, especially if I'm using all of my values in my chart. Well, if you didn't want to look at the chart and figure that out, the b minus a over n still works, right? So my b is 25, my a is 0, my n is 5, and so I get 5. You can tell that because you're counting by 5. 0 to 5 is 5, 5 to 10 is 5, 10 to 15 is 5, so on and so forth, right? And so basically what we have here is that, okay, again, you don't necessarily have to do this because it's given to us in the chart, but if I start at my A and I go to my B, which is 25, I'm going to have n equals 5 subintervals, so I'm going to write 4 tick marks here to create 5 subintervals, and if I start at 0, my next point will be at 5, my next point will be at 10, add 5 to that, 15, add 5 to that, 20, add 5 to that, we get to 25. It's these same values that I have in my table. And so what we're going to have here when we do our left-hand sum, remember this is our, we usually write t sub I, but this would be x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. When I do this estimate using 5 rectangles, notice this is all of our values are going to be multiplied by delta x. So I'm going to write that out. And this is basically going to be f of x sub 0. F of x sub 0 is 0. So I'm going to go ahead and say f of 0 plus f of x sub 1, which is 5, plus f of x sub 2, which is 10, plus f of x sub 3, which is 15, plus f of x sub 4, which is 20. And so this is what I want to calculate, all right? Now, my functional values are given on this second row here, right? And so this is going to equal, I'm going to come over a little bit. My delta x is 5, and I'm going to multiply that. Now I'm going to put the values of f of 0. Well, f of 0 is the output value at 0, which is 100. Output value at 5, 82. At 6, 69. At 10 is 69. At 15, 60. At 20, 53. When you multiply all of that together, we're going to get 1,820. So that's my estimate of my integral. Notice I put an approximation here because this actually equals our Riemann sums, which assumes that n approaches infinity, but we can't let n go to infinity when we have a table of values. The largest value of n that we can use in this example is actually 5. And so I go from I equals 0 to 4 to approximate this integral with my left-hand sum. I can do a very similar approximation with my right-hand sum. I'm going to go do the integral from 0 to 25 of f of x dx. I'm going to approximate it with my right-hand sum. That's going to be I equals 1 to 5 of f of x sub I times delta x. And this is going to equal my delta x. But now we start at f of x sub 1, which is f of 1. Sorry, it's not 1, it's f of 5. X1 is 5, as we can see from here, plus f of 10, plus f of 15, plus f of 20, plus f of 25. All right, my delta x is 5, and my other values are in my table. F of 5 is 82, f of 10 is 69, f of 15 is 60, f of 20 is 53, and f of 25 is 49. I used a parenthesis to open that, so I'm going to close it with a parenthesis. And when we're finished doing that, we get 1565. Now, we use a left hand and a right hand sum. A better approximation for the integral from 0 to 25 of f of x dx would equal 1820 plus 1565 all over 2. I didn't do that calculation, so I'm going to do it now. So 1820 plus 1565. We're going to divide that by 2, and a better estimate will be 1,692.5. All right, and that's how we can use our left and right hand sums to approximate a definite integral. Again, our goal is to let n approach infinity. When we're given a table of values and we're doing this by hand, we're not going to be able to go to infinity, but we still can get an approximation. All right, let's go to another example. It says use the graph below to estimate the integral from negative 10 to 15 of f of x dx. All right, so I have this table, this graph here, and I want to integrate f of x dx, right? Find the integral. Well, what I'm going to do is I'm going to use this grid here because it's helping me out here, right? I know I'm going to start at negative 10 and I want to go to 15, which is over here, right? 15 is over here. Now, if I want to find the integral, right, I'm going to come down here of negative 10 to 15 of f of x dx. The integral equals the area under this curve, right? So you can use these grids and estimate the total, these boxes or these squares in this graph to estimate the total area. It can get difficult, but if you do that, your approximation may be slightly different from what I'm going to do. But notice my x-axis is counting by 5s and my y-axis is counting by 5s. It's notated every 10th one, but they're counting by 5. If I wanted to estimate this integral, I can literally try to estimate the area under this curve by counting up the number of squares and then multiplying by the area of the square, right? Of the squares, right? Each square is 5 units by 5 units. So each square is 25 square units. So if I can count up the number of squares, now there are some partial squares, so you're going to have some fractional squares here, but you can estimate this integral by doing that. I'm going to stick to using the left and right hand sums because that's what we've been getting comfortable with. So I'm going to estimate this using my left hand sum. It's going to be the sum from I equals 0 to n minus 1. I'm going to count my n. My n is going to be the number of subintervals. Since this is counting by 5, I know that from negative 10 to 5, negative 5 is one subinterval. From negative 5 to 0 is a second subinterval. 0 to 5 is a third. 5 to 10 is a fourth. 10 to 15 is a fifth. So there's n equals 5. I'm going to use n equals 5. You could use more. You can say you're going to go from negative 10 to negative 7.5, and then from negative 7.5 to negative 5, and negative 5 to negative 2.5. I'm going to use negative 5. I'm going to use the grids, the tick marks that are labeled, right? And so my left-hand sum is going to run to 4 of f of x sub I times delta x. Again, I'm counting by 5, so delta x is going to equal 5. If you didn't believe me on that, you do 15 minus a negative 10. That's the b minus a over n, which is 5. That would be 25 over 5, which is, again, 5. All right, so my delta x is 5. My x of i's, I'm going to write it up here. I'm starting at negative 10. I'm ended up at 15. I'm going to write 5 subintervals because 10 is n equals 5. So from negative 10, I add 5 to that, I get to negative 5. Add 5 to that, I get to 0. Add 5 to that, add 5 to that, add 5 to that, I get there. right? And so this is going to equal my delta x. I'm going to start writing my delta x out front because it's going to be multiplied by all of this. My left-hand sum starts with 0, right? So this is x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, right? So it's going to be f of x sub 0, which is negative 10, f of x sub negative 5 plus f of negative or 0, 5, and 10, right? And so those functional values of the f of our function are actually the y coordinates on these points. So I'm going to highlight them, right? At negative 10, it looks like I have a y coordinate. We're counting by fives here of 5, right? So that's negative 10, 5. I'm only going to write the y coordinates here. At negative 5, the y coordinate looks to be close to 15. I'm going to say 14. At 0, oh, it's again close to that 15. So I'm going to say 14 again. At 5, oh, it's maybe about 12 if I'm estimating. At 10, I get this y coordinate, which again looks to be 14. And at 15, it looks to be right before 30. I'm going to say 29. All right. And so if my delta x is that, I'm going to come right down here. My delta x is 5. F of negative 10 is that 5. F of negative 5 is 14. F of negative 5 is, F of 0 is 14. F of 5 is 12. And F of 10 is 14. And so when I add those together, I get 295. All right, we can do our right-hand sums. To estimate this integral from negative 10 to 15 of f of x dx, again, we're going to use our right-hand sums here. So it's going to be the sum from I equals 1 to n. Our n is 5, f of x sub I times delta x. And so that's going to be our delta x. Our f of 1, f of x sub 1 is f of negative 5. Then we do f of 0, f of 5, f of 10, f of 15. All right. And since I open with a parenthesis, I'm going to close with a parenthesis. And so our delta x was 5, and our f of negative 5 was 14. F of 0 was 14, f of 5 was 12, f of 10 was 14, and f of 15 was 29. We add those together, we get 415. And so if I want a better estimate of this integral, I'm going to do 295 plus 415 over 2. And we get approximately 355. And so that's my best estimate. All right. And so again, you can use a graph to do this. You can use a table of values to do this, or I can give you a function. So look at this, right? In all of the other examples, I said, oh, the integral from like 1 to 4 of f of x dx. Well, if I know what my f of x equals, right? So here, I just said f of x here because I gave you the graph of f of x. In this example, I said f of x here is because I gave you the actual table. Now, what you can do, now I can tell you f of x equals some function, like 1 over the square root of 1 plus x squared. And then this is how we write the integral, because we know the actual expression that our function equals. And so instead of saying the f of x here, we have what f of x equals in its algebraic expression form. So this is the integral from 1 to 4 of 1 divided by the square root of 1 plus x squared dx. All right. Now, we've been able to do this before, right? We could do this using our left-hand sum, and I'm going to go over this really quickly. I'm only going to do the left-hand sum, right? I equals 0 to n minus 1 of f of x sub I times delta x, right? Now, what we have to do is we usually be given an n. When you're not given an n, you can choose your n. You want to choose an n that's reasonably big. I'm going to just randomly choose n equals 6, all right? That's a lot. It's actually still a lot, right? So my left-hand sum is actually going to go from I equals 0 to 5 of f of x sub I times delta x. Now, when I do this, I need to know my delta x. My delta x is b minus a over n. My b is 4. My a is 1. My n is 6. I chose that, and so I get 1/2. Notice my x-axis starts My A starts at 1 and it's going to end at 4, and I need to have 6 subintervals, right? Now it's going up by half. So this is 1 or 2 over 2. I'm going to write these in fractions. This is going to be 1.5 or 3 over 2. And then add a half to that. That's 4.5 or 2. 4.5 plus a half is 5 halves. Add half to that is 6 halves or 3. Add a half to that, you get 7 halves. Add a half to that, you get 8 halves or 4. So this 1 is your x sub 0. This is your x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and x sub 6, right? And that'll give you your 6 subintervals. 1, 2, 3, 4, 5, 6. You have 7 numbers, right? And so my integral is going to be found by me. I'm going to do my delta x, and I'm going to have f of x sub 0, which is 1. So f of 1 plus f of 3 halves plus f of 2 plus f of 5 halves plus f of 3 plus f of 7 halves. We know that our delta x, all right, this is kind of off to the side. We know that our delta x is 1/2, so we're going to have a 1/2 here. And to find these functional values, all we have to do is go to our calculator and plug in 1 into our function. So it'll be a 1 divided by a square root of 1 plus 1 squared. Well, 1 squared is 1. Add 1 to that, 2. So that's basically 1 over the square root of 2. All right, now these are going to get a little complicated, and the decimals are going to be pretty big, right? And so what I'm going to do is I'm going to, you can use your calculator to do this, right? So I can do 1 divided by second square root 1 plus 1 squared. Press enter, and I'm going to get 0.707, so on and so forth, right? And so that's what I'm going to get for that one. I'm going to put the decimal form. I'm going to write it to 3 decimal places because these are irrational numbers. And then I'm going to plug in 3 halves, right? So I'm going to do 1 divided by the square root of 1 plus, now this is a fraction, so I'm going to do 3 halves in the fraction and then square that, press enter, 0.555. Now I'm going to put 2 in there. 1 divided by second square root 1 plus a 2 squared, and I didn't put that in parentheses because 2 is a single number. I'm getting 0.447. All right, and you get the picture. You get the picture. You can do that, and you can continue. You add those numbers, you multiply by half or 0.5, and you're going to get your estimate here. All right, an alternative way to do that to show all of those sums is to use your y equals feature. If you have a graphing calculator. Now, if you don't have a graphing calculator, you have to do it the way I just did it. I'm not going to spend that much time going over that any further. I'm going to put the function in here into my y equals. And I'm going to press enter. Now, you could use your table feature, right? So I'm going to go to second table set. Our A in this example, we started with 1, so I'm going to start at 1. Our delta x was 1/2, so I'm going to put 1/2 in there. And I'm going to have this on auto, right? I'm going to press enter. And then I'm going to go to second graph to get to my table. And there you go, seeing those numbers again. This is a quicker way to get those numbers instead of plugging them in one by one. Again, if you don't have a graphing calculator, this is how you'd have to do it. But I get 0.707, 0.555, 0.447, 0.371, 0.316, and 0.275 for our last one, which is that 3 halves, right? An alternative way to do this is to let the calculator do it for you. So what I'm going to do is I'm going to go back to y equal and make sure my function is correct. I'm going to go and graph this. I'm going to graph it on my calculator. Now, this is my function. We're interested in the part of the graph from 1 to 4. Notice my function is very low to my x-axis. And so what I'm going to do is I'm going to change my viewing window. I'm going to start at 0, and I'm going to go to 5. Now, I know it wanted me to go from 1 to 4, but I want to see what's happening on the side a little bit, right? And I know that I'm not going to have any negative values because this thing was not negative. So I'm going to start at 0 and I'm going to go to 2. Notice that function was very close to my y-axis, right? Or my x-axis. I'm going to press enter for those and then go to graph. And now I'm going to see my function. And so notice that I said I was going from 1 to 0 to 5. So my integral that I want to calculate is going to be the area between my x-axis and this curve, which is here. Well, I can calculate an integral by looking at the calculate menu, right? So if you go to second, trace, option 7 is to do the integral. You know, you have integral of f of x dx. So I'm going to enter 7 or scroll down there. They're going to ask you your lower limit. They're using the limit because the numbers a and b are called limits of integration. Our lower limit was 1. So I'm going to go to 1 and press enter. Then they ask you for your upper limit. And so I'm going to go to 4 and press enter. And it's actually going to calculate that area for you. Now, actually, I'm going to let this go from on my y-axis from -2 to 2, so I can actually see the full graph with the shading going on there. Okay, and so we go to second, trace, option 7. Once again, I messed that up. Option 7, I'm gonna do my 1 as my lower limit, 4 as my upper limit, and see it calculate everything for me. Did I not go to 5? No, I went to 10. That's why it's doing that like that. All right. One more time. One, 4, press enter. There it is. And this is what my integral actually equals, 1.213. This is pretty much, it is an approximation because it's a long decimal, but it's the most exact approximation because it's actually doing the number or the mathematics to get you that integral there. And so this integral equals, I forgot already, 1.213 approximately. So the integral from 1 to 4 of 1 over the square root of 1 plus x squared dx is approximately 1.213. Again, of those of you who don't have a graphing calculator, when you do this here, you're not going to get 1.213, right? You're going to get this. You're going to have to find f of 5/2, 3, and 3.5. You go do your right-hand sum, do the average of that, and then you can get this 1.213. All right, but this is what we have in this video, and I'm going to stop this video now. We'll see you during our next video.